All right, let's get started with chapter 13, problem set number 2. First one is number 43. What linear speed must an Earth satellite have to be in a circular orbit at an altitude of 160 kilometers above the Earth's surface? Well, let's start with general principles here. We're talking about a satellite in circular orbit. So if you're in a circular orbit, so let's put the Earth on here. Here's the Earth, and if you're in a satellite and you're in circular orbit, you're going around in a circle. Therefore, there's a centripetal force, but that centripetal force is provided by the universal gravitational force. So mv squared over r, which is the mass of the satellite, the speed, and the radius of orbit, that's this whole radius here, is going to be equal to big G, universal gravitational constant, mass of the planet, mass of the satellite, all divided by r squared. Again, that's the radius. So I can see that these m's are the same, some of these r's are the same. So speed squared is equal to gm all over r. Now, it tells us that the altitude, so A for altitude is 160 kilometers, that number of meters. And so what is the r value here? Well, it's going to be the radius plus the altitude. The radius of the Earth, 6.37 times 10 to the 6th meters, plus my 1.6 times 10 to the 1, 2, 3, 4, 5. Put that in a calculator real quick. I got 6.5. So I'm going to plug that in there. So we're going to calculate the linear speed here. Now, we know the universal gravitational constant is 6.67 times 10 to the negative 11. And the mass of the Earth is 5.98 times 10 to the 24. So plugging these in, so this is v squared, so when you do this, don't forget to square root it, and I got 7.816 meters per second. Second part says, well, what's the period of that revolution? Well, as long as you're going around in a circle, shouldn't your speed equal to your distance, that's the circumference, divided by the time, which is the period? So if I rewrite that, period is going to be equal to 2 pi r divided by v. Put that in the calculator real quick. I got the time to be 5.247 seconds. And then if you divide that by 60, you get 87 minutes. Now, what I like about this is that this is an actual real height of a satellite. And so this thing only takes about 90 minutes to go around. So every 90 minutes, it's making a full lap around the Earth, which seems to me crazy. All right, let's look at the next one. We got problem 53. 53, let me get ready for that. 53 says a 20 kilogram satellite has a circular orbit with a period of 2.4 hours and a radius of 8 times 10 to the 6 meters around a planet of unknown mass. If the magnitude of the gravitational acceleration at the surface is 8, what is the radius of the planet? So there's two things going on here. I'm going to have to address them both. First of all, it's talking about a gravitational acceleration at the surface of 8. So remember from our previous studies that the local gravitational force is actually equal to the universal gravitational force. So the mass of the object is d, so if you want to find the acceleration due to gravity, you need g, mass of the planet, divided by the radius of the planet squared. Okay? So that we're going to hold on to that for a second. Another piece of information they're telling us is it's a 20 kilogram satellite. Let's write that down. Little m is 20 kilogram, has a period of 2.4 hours. Okay, so period is equal to 2.4 hours. But we don't work in hours, we got to work in seconds. So we're going to take our 2.4 hours, multiply by 60 to get minutes, and multiply by 60 again to get seconds. 8640 seconds. Okay? And the radius, okay, so this is the radius, not of the planet. Okay, this is the radius at the orbit distance. So this is the orbital radius of 8 times 10 to the 6th meters. So there's a couple things we can do here, okay? Let's go back and let's think about our general principles for orbit. I know for an object in orbit, the centripetal force is the gravitational force. Therefore, mv squared over r is equal to g, big M, little m, all over r squared. I can see that the mass of the satellite somehow disappears and one of these radii disappears. So I end up with v squared is equal to g m all over r. Now, because it's going in a circle, I know the speed can be calculated using 2 pi r over t, where that's distance over time. If I square everything in here, I end up with, 4 pi squared r squared all over t squared on the left side. And that's equal to gm over r. And I think the thing that we don't know here that we're missing is what the mass of the planet is. Because if I want to find, using this, if I want to find the radius of the planet, I need to know the mass and the gravitational acceleration. So if we can use this to find the mass of the planet, we can plug it in over here. So let's solve for mass of the planet here. So I end up with 4 pi squared, and this is going to multiply r times r and get r cubed all over t squared g. And that's going to be equal to the mass of the planet. And luckily, I know the radius of orbit, I know the period of orbit, I know g value, so we can just plug and chug and solve. All right, let's put it in the calculator and see. So I got the mass of the planet to be equal to 4.06 times 10 to the 24. And that's kilograms. And that's actually pretty close to the mass of the Earth. So that looks pretty good. It's very reasonable in terms of the sizing. And so we use the second piece of information to solve for the mass of the planet. Now we're going to go in and solve for the radius of the planet. If I rewrite this, r squared is equal to g over g. I know these two now, and it tells me in the problem that the acceleration at the surface is 8. So I can plug in the g value, which I know, the mass, which I solved for earlier. A was here, and then I'm going to have to take the square root. Let me calculate that real quick. And I end up with 5.82 times 10 to the 6th meters, which is actually pretty close to the Earth. The Earth is 6.37 times 10 to the 6th. So this is the planet here that's just a little smaller than Earth, but relatively close to the same density. And that was good. All right, one more, 57. In a certain binary star system, each star has the same mass as our sun. Okay, so let's draw a binary star system first. This is going to be challenging. So we got 2 stars, and we'll put one, let me draw the thing first. So they are orbiting since they are of equal mass, they are orbiting each other in a circle. So one of them is over here, and the other one is over here. And they're not really orbiting each other, they're orbiting the center of mass between them. But since they have the same mass, they're actually each going in their own circle around that. All right, and it says that basically mass 1 is equal to mass 2, which is equal to the mass of our sun, which I think is equal to, let me check, 1.989 times 10 to the 30th kilograms. All right, so here's our picture. The distance between them is the same distance between the Earth and the sun. What is their period of revolution in years? So the distance between them is the same distance as between the Earth and the sun. So this distance here is equal to the Earth-Sun distance. Now, that's interesting because when I look at this here, this is the radius. This is actually the diameter of these, and that's going to be important. This is the radius. So we're noticing that in this case, the force between these two is at a different distance than is the radius of their circle. And I think that's going to play an important part coming up here. So we want to know, what is their period of revolution in years? So let's start with our basic understanding of the forces here. We know that each of these is in a circular orbit. So the centripetal force is equal to the gravitational force. So if I look at either of these, I'm going to end up with mv squared over r, where v is the speed and r is the radius. But the gravitational force here, g, m1, m2, all divided by, and this time, it's not divided by r as it is in previous times. This time it's divided by d, which is the distance between them. Now, we're going to notice here that d is equal to 2r, and I think that that's going to be important for us coming up, but I just want to get this down first. So, what do we know and what are we looking for? So eventually we have to figure out the period, okay? So one of these m's can cancel because it was just for this. So v squared over r is equal to g m all over 2r squared. Now at least I have everything in terms of r, which is okay for me. So there's an expression for the speed. I feel pretty good about that. So if I know the mass of the sun, which I know, and if I know what did it tell me here? It told me that the distance between them is the Earth-Sun distance. So R is going to be equal to the Earth-Sun distance divided by 2. I'm going to have to look it up. So the Earth-Sun distance is 149.6 billion meters. So this would be 1.496 times 10 to the 11 meters. We're going to divide that by 2. So that's the R value here. So let me plug this in here and see if we can't solve for the speed. So I got that the speed is equal to 4.45 times 10 raised to the, oh, just kidding, I didn't square root. Let's try that again. Got a square root. 2.1 times 10 to the meters per second. All right, so now we have the speed. Don't forget that if you're going in a circle, speed is equal to 2 pi r all over t. Therefore, the t should be equal to 2 pi r all over v. So I have the radius here. I have the speed here. Let's plug in, check, and see what we get. So it's 2.22 times 10 to the 7 seconds. Divide by 60 to get minutes. Divide by 60 to get hours. Divide by 24 to get days. And divide by 365 to get years. And I got t is equal to 0.71 years. So I find it interesting, actually, that in this case here, this is the Earth-Sun distance. So if the Earth had a bigger mass, it would actually, instead of taking the full year for it to go around, it would only take 0.71 years to go around. And that's it for problem set number 2.